Welcome back, everybody. We're finishing up example 11.6. Actually, this looks like 11.5, but it should be 11.6 in your notes. And this is one we started actually in class together, and I promised that we would finish it up. So here it is. I have part A done already, which is the one that we did in class. And I'm going to go through part B, C, and D with you, which should actually go fairly quickly. We stated in part A that, or the question in part A, I should say, is what is the force exerted on the car by static friction? We've got a car going around in an arc, and what's keeping it in the arc? Well, some sort of centripetal force caused by something. Well, in the case of a car, the only thing that really causes the centripetal force to make it go around in a circle is the friction caused by the tires, or the static friction. And we calculated that. That was this right here, 5,642 newtons. And we got that by taking, we took the mass of the car times the centripetal acceleration, which we had calculated previously up here with the givens. Multiplied them together and got our static friction, or you might say our net centripetal force on the car. So part B is asking, calculate the angle that your dice make with the vertical. Now, if you're just coming back to this problem, you might say, what does that mean? Well, if you recall, we have a rear view mirror right here. Okay, it's a little off center. And as you go around the corner, fuzzy dice, which oftentimes people have hanging from their mirror, they're going to slide out to the left or to the right because, well, centripetal force is acting on the objects in the car, and it's going to actually push that off to the side. Okay, so B is actually asking us, what is this angle right here? What is that angle? Okay, well, if we think about it for a minute, let's turn this into a vector problem, because we have forces acting at different angles to each other, causing these dice to fly out. So let's turn this into a simple vector addition problem, where we're going to have a right triangle. It's not very right, but that'll work. And this is supposed to be a right angle, right here. Okay, that's not even a good right angle. There. It's still not good, but you get the idea. And at rest, our dice have a force acting on them, don't they? That's the force caused by gravity. And so at rest, or actually at all times, but we see it at rest, our dice have a downward force of mass times gravity. Okay, but now that our car is going around in a circle, or some sort of circular arc, we have a sideways force applied to it. And that's a sideways force that we call the centripetal force. Okay, now we calculated up here the net centripetal force on the whole car. And that was by taking the mass of the car times the centripetal acceleration. Well, we can do the same thing by finding the centripetal force applied to the dice. I'm going to write that tiny down here. Dice. Okay, well, what would the centripetal force applied to the dice be? Well, remember that centripetal acceleration, or any acceleration, it applies itself to all things equally. Like, for example, it doesn't matter how massive you are, the acceleration of gravity is 9.81 meters per second squared for you or for anybody else. Okay, so we calculated the force on the car by taking the centripetal acceleration, times the car's mass to get the force on the car. We can do the same thing by taking the mass of the dice, md, times the centripetal acceleration. Okay? That'll give us the net centripetal force acting on the dice right there, which will enable us to complete a vector diagram. So let's go ahead and let's calculate those out, actually. So mass of the dice times gravity. In fact, I'm going to write that up here. Mass of dice times acceleration of gravity. That is 0.11 kilograms times 9.81 meters per second squared. And that should give us 1.08 newtons. Okay? And while we're at it, why don't we calculate the net force, or the net centripetal force on the dice as well. So the net centripetal force on the dice, DCE, you get the idea. Dice equals mass of the dice times, not the acceleration of gravity, but in this case, the sideways acceleration of centripetal, or the sideways centripetal acceleration. Okay, that's 0.11 kilograms times, and we found this right down below here, 4.34 meters per second squared. Okay, so we got two forces acting at right angles. The vertical force of the mass times the vertical acceleration of gravity. And then we've got the horizontal force of the mass times the horizontal acceleration of, I keep saying that, the horizontal acceleration of centripetalness. How's that? Okay. Well, what does this come out to be? That comes out to be, and I have it here, 0.477 newtons if we multiply them together. So those are going to be the two forces in our vector diagram here. Still kind of a skewed right triangle, but you get the idea. So now it becomes simply trig. Our mg, that's 1.08 newtons acting downwards on our dice. Okay, and then we have a sideways force caused by, well, it's the centripetal force caused by mass times a sideways centripetal acceleration of 0.477 newtons. And if we want to find this angle right here, which is what B is really asking us, we can do that fairly easily. So we want to find this angle, theta. Theta equals, well, we don't know. Well, we have an opposite and we have an adjacent. So if we remember our SOHCAHTOA, that would say that the tangent of theta would equal 0 opposite 0.477 newtons over the adjacent 1.08 newtons. So theta would be the inverse tangent of that fraction. 0.477 divided by 1.08. And that would tell us that theta should be 23.8 degrees. I can do better than that. 0.8 degrees. Okay? There we go. There we have it. That's our answer to B right there. And I will box that. And we'll move on to C. And you're probably saying then, well, great, it's probably just as hard as B. Well, not necessarily. Because what we want to find out in C is, what is the tension of the string holding up the dice? Well, we've just about done all the work for that. I'm going to write C up here. Okay, tension, that's what we're trying to find out. Well, remember, tension is a force. And if we have a downward force and a sideways force, the resultant force would have to be that tension right there in the string. We've already calculated the forces, so we can just write them in. Again, this is 1.08 newtons, and this is 0.477 newtons. So this is our tension T right here. That should be easy to solve. Pythagorean theorem. T would have to be the square root of 1.08 squared plus 0.477 squared. So our tension should be 1.18 newtons. And that's it. Again, we did all the hard work in part B right there. So, part D. I'm going to write this right here. For part D, I'm going to refer back to this right here. This diagram in part B. And part D asks, it says, okay, you also have keys that are hanging probably from where you put them in the ignition, which are heavier than your dice. It doesn't say how much heavier, but it just says they're heavier or they're a different mass. They're also hanging off to the side as well. Compare the angle of your keys to the angle of your dice. Okay. Well, remember I said before that acceleration affects all things equally. Like you or a larger person or a smaller person are all affected the same way by gravity, 9.81 meters per second squared. So your masses don't really matter. So if we look over here, we could change to black. We could look at this diagram and apply this to the fuzzy dice. We could apply it to the keys as well. The masses do not matter. Now, they don't cancel out exactly, but we could just as easily have made a vector diagram out of simply accelerations. A vertical acceleration and a horizontal acceleration right here. This could be the mass of the dice. It could be the mass of the keys. It could be the mass of anything that is hanging down on a string. And if we have this vertical acceleration here and this horizontal acceleration right here, and we make a right triangle out of it, it will make the exact same angle every time. So that's going to be the same angle. I could prove it to you by making up a mass for the keys and doing the exact same thing, but you could do that yourself, honestly, if you don't believe me. But it's going to be the same angle for anything, because the centripetal acceleration, not the force, but the centripetal acceleration affects all objects of different masses equally. So there you go. That's example 11.6 finished up. If you have any questions, please come see me, but I hope that cleared that up for you. I'll see you on the next video.